Okay, we're going to continue on here, chapter 11. We talked a lot about waves. We saw a few formulas. C is equal to the wavelength times the frequency. We also saw energy is equal to h times the frequency. C is the speed of light, which, speaking of what we were just speaking about, 2.998, I think, is what they want you to roll with here, meters per second. Planck's constant, I'm gonna go with 6.63, but I feel like they want 6.626, but we'll go with this number here. And those are obviously two constants that you have available to you. Remember, the relationship between a wave and sort of energy is the shorter the wavelength, the higher the frequency, and the higher the energy, as opposed to the longer the wavelength, the lower the frequency, and the lower in energy. So why we're talking about waves is basically in our relationship here, what we're talking about is the idea of electrons as they transition from one energy level to the next. That would be an endothermic process where that's absorb energy to go to a higher energy level, but they will eventually want to kind of come back down in terms of energy, and that energy will be given off in the form of a photon of light, which is basically a wave. And depending on where that wavelength sort of comes off in that electromagnetic spectrum, again, we may see colors associated with it, maybe heat. It may come off really sort of anywhere in that electromagnetic spectrum. We could use these equations here to calculate both the wavelength or the frequency if you have one or the other. We could also calculate the energy associated with that wave coming off by using the one on the right there. We could also put them both kind of together here, since the frequency would be c divided by the wavelength. We can incorporate that into our energy one, where essentially the top is now all these constants that we have here, and the bottom is the wavelength. So if you know either the wavelength or the frequency of that particular wave, you can basically calculate the energy associated with that. We talked about sort of this idea that unlike sort of Bohr's model of the atom, where we have the nucleus and these electrons in these orbits, and there's sort of a known path of how they are traveling. We kind of moved away from that, as it didn't really hold up very well as we got past one electron, hydrogen, or anything with more than one electron. And then we kind of moved away from orbits and not really knowing how the electron is sort of moving or its position, and it perhaps moving fairly randomly about that sort of empty space. So the idea there of like Heisenberg's uncertainty principle was that the more you know the location of a particle, like say an electron, the less you know how it's moving, and vice versa. The more you know how it's moving, the less you know about its position. So Heisenberg, Schrodinger, and de Broglie, all of those sort of ideas came up with that the best we could kind of think about is probability, and the probability of finding an electron. And basically, a lot of probability sort of maps, if you will, are these orbitals. And these orbitals are what are referred to as atomic orbitals. And these are really, for all intents purposes, sort of probability maps of where you can find electrons within the atom. There are s orbitals, there are p orbitals, there are d orbitals, and there are f orbitals. We saw sort of their shapes, kind of a circle, teardrop, couple of teardrops together there, figure eight sort of happening there. Each individual orbital could hold a maximum of 2 electrons. And when we talk about the s orbitals, they do begin on the very first energy level, which is known as n is equal to 1. That is the principal quantum number. It is not until you get to the second energy level that you do start to see p orbitals occur. Uh, d orbitals don't occur until you get to the third energy level, and f orbitals not until you get to the fourth energy level. Now, when we talk about sort of s orbitals, there's basically just one type of s orbital, which means you basically could just put 2 electrons in there if those arrows are the electrons. On the second, there's also an s orbital. That's again where we start to see our p orbitals that happen. And as we talked about, if you take a group of orbitals, like a group of p orbitals, a group of d orbitals, or a group of f orbitals all together on the same energy level, that is sometimes referred to as a subshell or sublevel. And that is why when we say a p subshell can hold 6 electrons, that's because each of those orbitals can hold 2, and that's going to give us 2 times 3, which is 6. We also would have a d subshell that has 5 different types of orbitals. There's an f subshell that has 7 different types of orbitals, and obviously our p subshell that we were just talking about there has 3 different types of orbitals. That means, again, on any energy level that you find a p subshell, you can max it out with 6 total electrons. It doesn't mean you necessarily have to use all 6 electrons or put all 6 electrons in there, but you can max it out. Any energy level where there are a d orbitals found, you can max out the d orbital subshell or the d subshell with 10 electrons, 2 in each. And any energy level where there are f's, you can pretty much max out at 14 electrons if you fill the entire subshell or sublevel. Remember, sort of the other terminology that you sometimes will hear with this is if you take an entire sort of energy level, that is what is referred to as either a level or a shell. And that basically would encompass any orbitals that are pretty much on that energy level. So in the case of the one I just did there, that would encompass the s orbital in addition to the 2p subshell. All 4 of those orbitals, each could hold 2, would give you 8 total electrons if you filled that up. You could calculate the maximum number of electrons on a shell or level by using this formula. You take the principal quantum number, you square it, times it by 2, and it'll tell you if you wanted to max out a particular energy level, how many total electrons you could put in there. Any questions on that stuff there we talked about last time? All right, so we're really sort of leading up here to electron configuration. And as I mentioned before, if you want to write electron configuration, again, knowing the maximum number of electrons that you could put into an orbital or a subshell is really important. We'll talk a little bit about the energy of these orbitals. And here's what they look like. Again, on our n equals 1, we have just our s orbital. And a reminder that the principal quantum number pretty much goes to 7. So it's like 1 through 7. N equals 1 is the closest to the nucleus and lowest in energy. As you go above that, things get further away from the nucleus, a little higher in terms of energy. When we look at where the placement of all these orbitals are in terms of their energy levels, this again would be our n equals 1, our n equals 2, n equals 3, n equals 4, and so forth. What we see is on any energy level in, say, hydrogen, when there's only 1 electron, all the orbitals are pretty much identically placed in terms of energy. And what I mean by that is everybody on the 3rd energy level is sort of equal. The s's, the p's, the d's, the s and p's on the 2nd, and so forth. And that's really important for how electrons go in. As I might have mentioned last time, electrons essentially will always go into the atom on the lowest energy level. And as that gets filled, they go to the next lowest. And as that gets filled, they kind of keep progressing on until they sort of populate all the electrons that they need. Now, when we start to move away from hydrogen and we get a lot more electrons involved, because there's a lot more electrons involved and electrons really don't want to be near other electrons, for example, there's actually some shifting that occurs in the energy levels of these orbitals. And what we see is something like this. And the major sort of shift that occurs is as we go from 1s, then the 2s would be lower, then the 2p, then the 3s, then the 3p. It's actually right here. Actually, what happens is with all those extra electrons, it is actually the 4s is actually going to be lower in energy than the 3d. So as electrons go into the atom, They will come through and fill everything below. They will fill up our 3p. Then they will actually fill up the 4s before they start to move over to the 3d. That pattern also holds as you continue on. Again, we see kind of our 4p, we go to 5s, back to 4d. So there's sort of this kind of change that occurs in the energy of these orbitals when we get lots of electrons involved. They're no longer perfectly equal with each other. So it's really important to know the order at which electrons go into the atom. And this little guy right here will basically tell you the order of how the electrons go in. And if you know this, and you know what we talked about, that if you max out a s orbital, that's 2 electrons, a p subshell, that's 6, a d subshell, that's 10, and an f subshell, that's 14 electrons. You pretty much can write any electron configuration that you want. How this thing works is you always start up here. So this is always your starting point. And then you pretty much just follow the arrow. So the first place you would go would be the 1s. When you get to the end here, you just kind of zigzag back and come back around and just keep following the arrows. When you get to the end here, you zigzag back this way and you keep following this. So why this is really good is this is something that, frankly, you can recreate yourself on the paper very easily by remembering pretty much the 4 things that we talked about, which is where each of those orbitals begin. And what I mean by that is our s's begin on the first energy level. So you write like a 1s. Our p's don't begin until the second energy level, so you go down a little bit to the right there and put a 2p. Our d's don't start until like the third energy level, so you come down over to the right and go 3d. And our f's don't start to the fourth energy level, come down, go over to the right a little bit, go 4f. At that point, you pretty much just fill in the numbers underneath. You just go like 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 5f. Even if you put a little bit too many numbers down here, it's not going to make a big difference. You'll never get there anyways in most cases. So you can recreate this really easily. And now you pretty much have the correct order of how these electrons go in. And as you can see, our 3p to our 4s, and then back here. So that's a really good way to sort of recreate this yourself. And all you have to do is remember essentially where each of these orbitals basically begin and kind of put them on a diagonal and just fill in the numbers basically underneath there. Any question on that there? Okay, so let's talk about electron configuration and sort of how to write electron configuration. And here's a picture for your book that shows you the order that's happening there. Electron configuration tells us how the electrons are distributed within the atom. We typically write in this class and in most chemistry classes that you sort of write electron configuration for is you write electron configuration for filling order, how they kind of fill into the atom. We don't usually write electron configuration based on energy, which is slightly different. The number of electrons in a neutral atom will equal the atomic number. Again, the atomic number is the number of protons, which are the positively charged guys. So if we have a neutral atom, that will also be our number of electrons. So let's take a look at this and once again talk about how we can do this. Again, if we look at hydrogen, its atomic number is 1, which means it has 1 electron. So if we come back to our little chart here, we're going to again start up here, and that will take us right to there, which is our 1s. And what we would write then is the electron configuration would be 1s1. And the 1 in the front is the principal quantum number. It's the energy level. That's that N number. And it's basically the energy level. The letter there is the orbital or subshell that the electron's in, and the superscript up on top is the number of electrons in that orbital or subshell. And that is how you sort of say it, 1s1. That is how you write it as well. There's no commas, no dashes, nothing like that. And again, the first one is a regular size one. The S is a lowercase s, and it is a superscript up there on top is where you have to put that one. Now, we could also sort of show electron configuration by what is referred to as orbital diagram. An orbital diagram will typically use either a box or a line to represent the orbital, and we typically use an arrow to represent the electrons. So in this case for hydrogen, we just have a 1s box, and we would need one arrow. The first arrow always points upwards. So the first one always kind of goes in upwards, and it always sort of points in that direction. That is, as we won't get too much details, what is known as ms, which is the spin quantum number. And that has a value of +1/2 when you kind of put the arrow going in the forward direction or upwards direction in this particular case. Any questions on that there? Now, when we think about sort of what's going to happen next, and we think about where we're going to put the near electron, because that s orbital has room for one more electron, we really have two options as to how we can, for example, in any orbital, put the next electron. We could put it going in the same direction. We could put it going in opposite directions. And basically, there is a rule which is known as Pauli's exclusion rule, which basically says that no two electrons that share the same orbital can have the same four quantum numbers. And you may be going, there's four quantum numbers. There are. There is N, which is, as we've been talking about, there's N, which is that principal quantum number. There's L, which is basically going to tell you the orbital it's in, the type of orbital it is. There's M sub L, which will tell you how many orbitals there is and what orbital it's actually in. And there's M sub S, so that's the spin quantum number. Those are what is referred to as the four quantum numbers. And just to show you why we would not do the first one, as you can probably imagine, since they're heading in the same direction, they actually will have the exact same four quantum numbers. And if we did this electron here, the N value would be 1 because it's on the first energy level. The L value will be 0, and 0, by the way, for an L represents that it's in an s orbital. It's basically what the 0 sort of represents. The M sub L, which is the third quantum number, would be 0, and the M sub S would be +1/2. Now, obviously, this guy's pointing in the exact same directions, which means he will have the exact same four quantum numbers, and that would be a violation of Pauli's exclusion rule. So the way that we sort of get around this is when we put our first guy in, which again will have these four quantum numbers, and we put our second guy in, now because we put it heading in the other direction, it will have an N value of 1 because it's on the first energy level. It will have an L value of 0 because it's frankly in an s orbital. It will have an M sub L because there's only one type of s orbital. But because it's pointing down, it will actually differ from the first electron in its spin quantum number. It will have a -1/2. And because of that slight difference in the spin quantum number, these two electrons now will have different quantum numbers, and they will not violate Pauli's exclusion rule. So we're not going to get too deep into quantum numbers, but that's the idea behind it. So really the idea here that you should take away is when you're filling your electrons into an orbital, first one always goes upwards, which is that +1/2 spin. The second one goes downward, and that's how electrons should always fill an orbital. This, by the way, as we will see, is what is referred to as being paired the spin. They sort of cancel each other out. One's +1/2, one's -1/2. So they sort of cancel out their spins in that orbital. Any questions on that there? So that happens obviously with helium. So once again, I'll just do a partial of my chart here to get us through where we're at. So we're starting up here, we're going this way, and that's going to give us now a 1s2 in this case, would be the electron configuration for helium as it has 2 electrons. When we look at our orbital diagram, again, we want to make sure we do not violate Pauli's exclusion rule. So the first one always goes upwards, the second one will go down. And once again, that is what is referred to as having paired spin. Can I put any more electrons into my 1s orbital at this point? I cannot, right? It is filled, which means if we're going to our chart, we would need to zigzag back this way here. And the next electrons will have to go into the 2s orbital. So again, I guess I put the start too slow there, start there. And we would zigzag back into that. So let's see when that happens going through our periodic table. That's going to happen at lithium. So once again, we have our 1s, 2s, 2p, 3s, 3p, and so forth. So we're going to start up here. So that's going to give us 1s2, and lithium has 3 electrons. If you're not sure how many electrons you've used so far, you can just count the top number, that is 2. We then will have to zigzag back this way and go 2s1 in this case. And again, here, there's no dashes, there's no commas, no weird things that people like to do. It should look exactly like that. This, by the way, means that on the first energy level, how many electrons do I have? 2 electrons, yeah. And then on the second energy level, I have 1 electron, yeah. So grand total of 3. So that last one is the higher energy level electron. If we look at our orbital diagram here, we would need 2 boxes, one for the 1s and one for the 2s. And they would go in like this, again, up and then down. And now we will fill this next one here in the upwards direction. We can now see for our 2s orbital, we could put how many more electrons? 1 more electron, right, before we're full. So let us continue our path here. And that happens at beryllium, which has 4 electrons. Once again, if we just kind of make an abbreviated version here of our table or our chart, again, we're going to start up here. So that's going to give us 1s2. We're going to zigzag back this way. That's going to give us 2s2. And again, we could count up our top numbers there. And that is 4, which is what we need to distribute. Here again, we will have a couple of boxes there to represent each of the orbitals. By the way, I'm just going to go kind of left to right with these boxes. If you were drawing them correctly in energy, really the 2s box should go on top of the 1s. So really, if we were kind of doing this right in terms of energy, that's sort of how the boxes should look. I'm going to save space, so we're going to do it based on saving space rather than energy, but the 2s should obviously be higher. The first one will go in like this, second one will go in like that, next one will go up, and fourth one will go down at that point. And again, at this point, we are now filled our 2s orbital. That means we have to kind of zigzag back, and the next place that we will go is going to be our 2p orbital as we kind of keep zagging back there. So let's continue on here. Number 5 up there on the periodic table is boron. So again, it does have our 5 electrons. And again, starting up at top, going to give us 1s2, zigzagging back, going to give us 2s2. And now, as I mentioned, we do need to come to here. And in this case, we only need 2p1 at this case. I have how many electrons on the second energy level now? I have 2 and 1 more makes 3. They are both on the second energy level. And again, that is what the 2 represents. That's on the n equals 2 level. This is the first energy level. N equals 1 has still the 2 electrons. Now, if we take a look at our orbital diagram in this particular case, We will actually need a few boxes. And again, we're just gonna go sideways versus upwards. We will go up, down, up, down. And now we have these three boxes, and these three boxes represent the p orbitals. That's like our px orbital, py orbital, and our pz orbital here. And again, that's why we have our three boxes. Each box would hold 2 electrons, which means that's 6 total if we fill up that subshell. The first electron will go in left to right, and it will go in as we've been doing in the upwards direction in this case. Any questions on that there? Now, at this point, we actually can fill this p subshell with 5 more electrons before we have to move on to the next orbital. And we do have some options at this point in terms of how we need to fill that. And that brings us to another important rule in terms of how electrons are filled. So if we just look at our p orbitals here, we can do one of two things. If we are going to put the next electron in, you may want to pair it up like that. The other option would be to actually not pair it up and go next door. And Hund's rule states that the most stable arrangement for electrons in a subshell is one where we have the greatest parallel spin. So if you remember, this type of spin where they are matched up is called paired spin. Parallel spin is this situation here where everybody's heading in the same direction. So based on Hund's rule, we would not want to, in a situation where we have multiple orbitals in a subshell, we do not want to just pair it up front. The way we can maximize parallel spin is to basically fill each of the orbitals with 1 electron all heading in the same direction until we really have no more options at that point. Then we could come back and start pairing them up. So that is how electrons go into, again, subshells where there's multiple orbitals. We put in 1 at a time, and then we come back and pair everybody up until they're all filled. So that is the proper way, again, to sort of fill up like a P subshell here in this particular case, even a D subshell or an F subshell. So always goes in first upwards way there to maximize the parallel spins, and then we come back and start pairing things off if necessary. So that happens around carbon, which has, again, 6 electrons and also 6 protons. And again, just taking our abbreviated chart here, we're going to start up on top always. So that's going to be 1s2. That will fill that. We're going to zigzag back 2s2. We're going to come here to our 2p2. Once again, if we just count up the top numbers, they don't need to be circled, by the way. We're just counting up the top numbers, and that is 2, 4, 6. We will have our same sort of orbital diagram that we just looked at with our 3 boxes there, our lines to represent our p orbitals. And again, we're going to go up, down, up, down. First one goes left, next one goes to the center. And again, we're going to maximize our parallel spins first before we come back and pair them off. Any questions on that there? Okay, then let's continue out the last 10 or the first 10 here, and we'll continue on here with nitrogen. So again, for our nitrogen, we're going to start up here like we've been doing. And that's going to give us a 1s2, 2s2, and 2p3 as we continue to zigzag this way. We are now, as you can see here, pretty much halfway filled with our p subshell. And if we were to draw our orbital diagram in this case, we're going to go up, down, up, down, up, up, and up. At this point, we pretty much have maximized our parallel spin. There's nowhere else to go upwards, so any more electrons that will come in will now go back left to right and start pairing them up. And again, this representing our px, py, and pz orbital basically happening in that case. So continuing on here with oxygen, which is 8 electrons, we'll continue with our electron configuration, 1s2, 2s2, 2p4 in this case. So we're getting close to that maximum 6 for the subshell here. And again, continuing on with our orbital diagram, we're going to go up, down, up, down, up, 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 and now back to the left there. And we're going to pair off that first one. That's still going to sort of maximize the parallel spin that we could get at this point, which is those two guys to the right. Question on that one there. All right, so number 9 there should be fluorine. And again, continuing on, 1s2, 2s2, 2p5 in this case. We now have, by the way, 5 and 2, which is 7 electrons on the second energy level, and 2 electrons there on the first. And filling in our orbital diagram at this point, we're going to go up, down, up, down, up, 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 and down in this case. As we could clearly see, we have room left in the subshell for one more electron before it's completely filled and before we would have to kind of continue on to our next orbital, our subshell. And that happens at neon, which is 10. And that will get us 1s2, 2s2, 2p6. Again, if you count up the top numbers, that is 10, which is how many electrons you basically distributed. And now we could get to our orbital diagram here. And we're going to go up, down, up, down, up, 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 and then down, down, and down in this case. At this point, again, we have sort of maximized here. So we have done this, we have done this, we have done this. The next place there we will go, right, will be our 3s as we continue through our electron configuration. Any questions on that one there? So why don't you write the electron configuration for argon and see what you come up with. Argon's 18. Okay, so let's take a look. Again, we're going to start with, since it does have 18 electrons to match its protons, we're going to start up here. So our electron configuration here going to be 1s2, 2s2, 2p6 as we kind of zigzag through here. That again, if we count out the top numbers, is 10. We then would have to go to 3s, which we can put 2 in. That's now 12 electrons, which means we need to come here, and that's going to give us a 3p6 in this case. And that should be 18 electrons in this case. Any questions on that there? And our orbital diagram obviously will have all of our guys there. And again, this would fill in like we talked about, up, down, one at a time. It'll come back and fill, up and down. And again, same thing here, one at a time, and then come back and fill it up there. Okay, so any questions on that one there? So if we look at, for example, the electron configuration for potassium, which is number 19, and the way, again, electrons are pretty much added to the atom is in this buildup principle, which is known as the off-ball principle, and that's how protons are added to the atom one at a time in the nucleus. Electrons again go in lowest energy to highest until you're done, basically, and it kind of fills it up. And if we look at something like our potassium, as we talked about, that's the point where we do see that kind of switch is going to happen in terms of where you might think the electrons will end up. So again, with something like potassium, as we just saw, we come through here to here to here. That's going to get us to basically argon, and one more is going to be potassium. Again, we're going to go to our 4s, which again is lower in energy than the 3d, so they will get the electrons first as they do come into the atom. So if we write the electron configuration for potassium, it will look like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now, as we just saw with our electron configuration that we wrote for argon, that is pretty much right up to that point. That point right there is pretty much argon's electron configuration. And because of that, you could actually write a little shorthand for the electron configuration where you put in brackets there argon, and you continue on with the electron configuration. So this guy here means that we have argon's electron configuration, and then we continue on with it. Now, argon is a noble gas, and when you do this, the thing that should go in the brackets there is always the noble gas that comes before whatever you're writing. So for example, if we looked at sodium, which is 11, you could write 1s2, 2s2, 2p6, 3s1. Once again, if we just take this part of the configuration, that if we count up the numbers up on top is 6, 2, and 2, which is 10. And 10 on the periodic table is our friend neon. And we would put neon in there, which is a noble gas, and we would continue on with the electron configuration. So it's sort of a shorthand, and it should always be a noble gas that goes in the little bracket. And again, it should always be the noble gas. If you look on the periodic table, that comes right before whatever sort of electron configuration you're writing. Any questions on that? Now, let's talk a little bit about transition metals. Transition metals are obviously between group 2 and group 3 on the periodic table. And transition metals have incompletely filled D subshells, or give rise to incompletely filled D subshells. There are kind of two exceptions. There's really more than two, but there's two that you typically are sort of responsible to know in terms of normal electron configuration. And that is chromium, which is number 24, which has 24 electrons, and copper, which is basically 29. So if you follow our sort of chart there, and you did our little movement here, that might be enough almost to get me there. 4s, I think, should perhaps do it. If we did say chromium, which is 24, you would come this way, and we would have 1s2. You would come this way, 2s2. You would come that way, 2p6, 3s2, 3p6, again to our 4s2, and then to our 3d4, and that would be 24. And if you follow the zigzag approach for copper, you would get a similar type of deal, which is 29, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. If you did that, again, just strictly following the zigzag approach. Here up to this point, as we just maybe saw, that is argon's configuration, which is where the sort of shortcut there comes into play. So that is argon. Now, what has been found experimentally is actually it is more stable with one less electron in the s and one of those electrons going into the d. So these are the exceptions. They actually have one less electron in the s orbital and one more d electron in the d. They're able to do that because the 4s orbitals are lower in energy and our 3Ds are pretty much right next door, pretty much here. So they are very close to each other. So what happens is this electron, it's not that hard for it to sort of jump up there to the higher energy level, and just found to be more stable. If you think about it as well, by doing so, that's going to maximize a lot of parallel spins. So that's going to make it a little bit more stable as well. That's going to happen. Just so you know, to hopefully not further confuse the issue, what actually happens with those orbitals, by the way, is once you actually start putting electrons into the d orbitals, they actually switch places in terms of energy. And what ends up happening is the 4s actually becomes higher in energy than the 3d. So on the way into the atom, the 4s orbital is actually lower in energy than the 3D. But once you start populating the 3D with some electrons, there's actually a switch that occurs and they flop places in terms of energy. And that's what I was talking about a little bit earlier when I was talking about that we write electron configuration based on filling order and not energy. So if you look up somewhere online, you might sometimes see people write electron configuration where all the numbers are like kind of go in order. So they would write it like, 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s2. And that's written based on energy, which is what happens after electrons are in there. We don't write electron configuration like that in pretty much any chemistry class that you take. I've only took one where you do it that way. But you usually write it based on filling order, which is that zigzag sort of approach that we've been doing. So the two exceptions that you are responsible for is chromium and copper. And again, the exception happens at the end there. There's one less electron in the s orbital, one more electron in the p orbital, I'm sorry, the d orbital. In reality, as we'll see a slide, I think if you look on the periodic table where chromium and copper is, and you go below them and kind of in, there's a ton of exceptions, like silver's an exception, really. All those guys kind of below chromium, copper on the periodic table, down and kind of in, they all have some exceptions. Like PD up there, it's got like no electrons in its s orbital. They've all jumped up to the d orbital. So there's a lot of sort of exceptions that happen in the transition metal region. But for us, those are the two that you should definitely know. And there they are right there. And as I mentioned before, here are a few others which you, again, are not going to be responsible for, other than obviously these two that we were just talking about. But again, if you look on the periodic table, you can see that's sort of where they're located, below chromium and copper. And that was the one I was just talking about. It actually has no electrons in the s orbital. They've all been sort of promoted upwards to the d orbitals. Any questions on that? Now, the lanthanide series is basically the two bottom rows there, and that's where our f orbitals basically begin. So they have incompletely filled f orbitals that happen there. So let's talk a little bit about the periodic table and the electron configuration. If you know what you're doing, you can use the periodic table and actually count off electron configuration. So there are 7 periods. Those periods are the n numbers, like n equals 1, this would be n equals 2, and so forth. The first 2 groups are the s block, and s could hold 2 electrons, that's 1 and 2. Groups 3 through 8 is the p block, and p could hold 6 electrons, 1, 2, 3, 4, 5, and 6. The transition metals are the d block. They could hold 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And down on the bottom is the f orbitals. It could hold 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So for example, you can literally sort of count off the electron configuration. So for example, if we went to sodium that we just did, we would start up here. This would be 1s2 to there. This would then be 2s2 to there. This would be 2p6 to there. And this is now 3s1 in this case. So you could actually just count it off. Now, if you wanted to go to, let's say we wanted to go to sulfur, for example. right there. We would start at the top. That would be 1s2 to there, 2s2, 2p6, 3s2, and this is 3p1, 2, 3, and 4, and it would be 3p4. So it works pretty well. Problem though is, let's just say we wanted to go to our friend. Let's say we want to go to iron, which is like right there. So we would do, starting at the top, 1s2 to helium, 2s2, 2p6, 3s2, 3p6. This is now 4s2. This is where the D's start, right? The D's start at what energy level? 3. So this is actually not 4D, that's 3D. Yeah, that's 4D, that's 5D, that's 6D. So this would be 3D, 1, 2, 3, 4, 5, and 6. The D's are one behind the period number, so you got to keep track of that. Otherwise, obviously, you don't want to go 4D there. Also, the two bottom ones there, this is 4F, which really goes on the 6th energy level, and that is 2 behind the F. So it gets a little kind of crazy in this area here if you're not really careful. I would recommend the zigzag thing that we were using for electron configuration, but if you want, you can count off on the periodic table electron configuration if you wanted to do that. Again, you just got to be careful that, you know, this right here is 3D, again, 4D and so forth, and this is 4F and 5F here. So it is a little bit behind the period numbers when you get to the D's and the F's. But if you want, you can just count it off as well. Question on that there. All right. We're laying it up there for today, I think. Yeah, why not?